My name is Katerina, and I will talk about task 3 of the CHiME8 challenge. We call this task multimodal conversations in smart classes. And as the other tasks, we deal with multi-speaker speech recognition. What is unique about our task is that we focus on the use case of smart classes, which brings some new problems, some new research opportunities that we hope to promote by organizing this challenge. You can move on to the next slide. In the dataset that we collected for this challenge, there are two-sided conversations. So conversations of two people where one of the persons is wearing smart glasses that are capturing the scene. There are over 500 recordings with more than 100 speakers. And each of these recordings is accompanied by transcription and by speaker activity labels that were both manually annotated. Next slide. So let me talk a little bit more about the classes that were used to record the data. The dataset was recorded with ARIA smart glasses. ARIA is a research prototype that was created to support the research in this area. The glasses are equipped with various sensors. Importantly, there are 7 microphones at different positions of the glasses that capture 48 kilohertz audio. There is a camera capturing video, and there are different inertial measurement units, for example, accelerometer and gyroscope, that can help with giving some information about the movement of the wearer of the glasses. All of these modalities that are mentioned and that are emphasized on the slide are available in the data and can be used to build the systems in the challenge. Next slide. Here is an example of one of the recordings from the data set. Yeah, I think we cannot hear the sound, but then maybe just... Oh, okay, now we can.
Sure. What type of souvenirs do you usually get? Because we have the fridge magnets, we have T-shirts, we have cups, we have mugs. Yeah,
Maybe
we have
that's enough
everything.
just
So,
for an
what
example.
usually?
Um, just one thing that I want to note about the video. So you could have noticed that in the video, the speaker has a blurred face. This is the case for all of the recordings that we have in the data set. And we know that this complicates application of some conventional audiovisual methods that usually rely on the lip movements. But the face blurring is necessary because of privacy reasons that are very important to us. And we believe there is still some interesting information in the visual modality, for example, the gestures of the speaker or the movements of the camera itself that could help with speaker attribution. And we think that it can actually open some opportunities of leveraging other types of visual information than the lip movements. Okay, next one. There are different research challenges and problems in our task, and I will emphasize 3 that I think are somewhat unique to our task. First is the fact that everything is recorded with the smart glasses, which brings some new problems, such as the fact that all the sensors, including the microphone arrays and the camera, are rapidly moving with the movement of the head of the wearer of the glasses. Second, there are the multiple modalities available, so this opens the way to investigating effective combinations of the modalities for the task of speaker-attributed speech recognition. And third, for the application of smart glasses, it is quite often important to create systems that are fast and that act in a streaming fashion. And for this reason, we decided to focus on streaming systems. And in the challenge, we will also evaluate algorithmic latency of the systems. And if you move on to the next slide, this is something that I want to devote a bit of time of this talk to, because I think the evaluation of the latency is something that is a bit different in our challenge, and it is something that we get many questions about. So I wanted to give some time in this presentation to explaining this. So in this challenge, we asked the participants to provide a hypothesis for each recording, such as this sequence of words that you can see on the slide. And for each word, we want to have attribution to one of the two speakers, self as the wearer of the glasses or other as the conversational partner. And importantly, for each word, we also want to have a timestamp. For example, here, if you look at the timestamp that has the arrow on it, here the timestamp for the word was is 6.10 seconds, which should represent that the system has seen 6.10 seconds of the input signal when it decoded the word was. So for the system, anything that comes in the signal after 6.10 seconds should be irrelevant for decoding this word was. In the left bottom corner, there is an example of how to get these timestamps in the example of system which does chunk-based inference. So in this example, the input signal is divided into chunks, which are 1 second long, and the system processes these chunks independently. For example, the word good, which is decoded in the first chunk, should have timestamp of 1 second, because that is the end of first chunk, and the system has seen 1 second of the input signal when decoding the word good. The word evening is split into two subwords, where the last subword is decoded in second chunk, so the word evening should have timestamp of 1.9 seconds, because this is the end of the second chunk, and again the system has seen 1.9 seconds when decoding the word evening. With the scripts that we provide, we also provide a test script for testing whether your system is streaming and testing whether the timestamps that you provide are correct. And the test works by forwarding a signal through the system twice, where the second time the signal is distorted from some time onward. On this example, right bottom of the slide, the signal is replaced with random noise from 2.8 seconds onward. And if the timestamps that are provided are correct, it means that all of the words that had timestamps smaller than 2.8 should stay exactly the same in the second forward pass, because everything that comes after 2.8 should be irrelevant for the system to decode these words. It is very good to use this test to test the system, because it is very easy to overlook some aspect of the system that makes it non-streaming and that makes it use some future information, and this test can help to uncover this. Maybe still a little bit more. I'm spending a lot of time here, but I think it's quite important. So given this timestamps, what we do is that we will make a difference with Oracle timestamps, and using that compute mean latency and categorize the systems into 4 categories based on the 3 thresholds of the mean latency. And if you are somehow uncertain about how to define the timestamps for your system or for your style of inference, then please contact us and we can discuss it and figure it out together. Okay, that is it for the latency. Besides the main dataset, we have also published a multi-channel audio conversation simulator dataset and tools. The data contain room impulse responses and acoustic transfer functions that were recorded with the same classes as the main dataset. And the tools then make it possible to simulate conversations. So you can take publicly available speech and noise dataset and the provided room impulse responses, and using the tools create conversations that are hopefully similar as actual conversations recorded with the classes. This can be used to extend the training set, and in one of the baselines that we provided, we are using this, so you can use the baseline as an example of how to use these tools. And for the final slide, here are some links to the datasets and to the website. Please note the postponed dates for the submission, which is the same also for the other tasks. So now the submission deadline is July 17th. And I would just like to encourage everyone to participate in our task. Thank you, and thank you, Michael, for sharing the slides.